In this video, we'll talk about bases. We'll talk about what things are strong bases and what things are weak bases and how they react, and remind ourselves about some of the naming of those compounds. So if we start with what we consider strong bases, right? The thing that we normally associate with being strong bases are soluble metal hydroxides. Right? Now, the important thing here is soluble. If you remember solubility rules from General Chemistry 1, most hydroxides were insoluble in water, right? The exceptions were things that had to do with the alkali metal rule. That is, most alkali metal compounds are soluble. So alkali metal hydroxides are soluble. That would be sodium hydroxide, potassium hydroxide, lithium hydroxide. Right? So our alkali metal hydroxides are soluble. If they're soluble, right? Remember, soluble means they dissociate 100%. They dissociate when they dissolve. They are ionic compounds. So those soluble alkali metal hydroxides, right? That alkali metal solubility rule supersedes most hydroxides being insoluble. The other group, right? We've got semi-soluble group 2 metals, right? So that's barium hydroxide, right? Strontium hydroxide, and then calcium hydroxide. But we have to remember, right, that calcium hydroxide has limited solubility in water. So calcium hydroxide, you can't get much of it to dissolve, but the part that does dissolve dissociates completely, and therefore it acts like a strong base, right? So our first group of strong bases are the soluble metal hydroxides, right? And so we need to remember our soluble metal hydroxides, right? So our next group of strong bases are, let's go brighter color here, oxides of those same metals. Okay? So that would be something like, and we talked about this before, something like, the potassium oxide that you might find in wood ash that we dissolve in water and boil to make lye. So if you take potassium hydroxide, if you take these oxides and put them in water, the oxide reacts and you get 2 potassium hydroxide in aqueous solution. So oxides of those same metals react with water to make the hydroxides of those metals, making them strong bases. So the oxides of alkali metals, and then barium, strontium, and then calcium, and we always have to remember the limited solubility of the calcium hydroxide. Our third group of compounds that are strong bases are metal hydrides. Right? So metal hydrides, remember IDES? IDES means we're dealing with a negative ion, and this is telling us it's a negative ion of hydrogen. If we make a negative ion of hydrogen, well, since the nucleus is just one proton, that's positive, we need 2 electrons. So it is the hydrogen atom plus 1 electron. It's an H minus, okay? And so if we end up with something, right, like sodium hydride, if we react that with water, right, the hydride ion acts as a Bronsted-Lowry base and takes a hydrogen ion from the water, and so you end up with, right, the hydride plus a hydrogen ion making hydrogen gas, right? That leaves behind a hydroxide ion in aqueous solution, and then we have the sodium ion around, and so we end up with the equivalent of a solution of sodium hydroxide in water, and then we lose the hydrogen gas can bubble out of solution. So metal hydrides can react in water, right? They react 100% to make hydroxide ion solutions in the water with a yield of 100%. So those act as strong bases. Our last group of species that will act as strong bases are compounds that are anions of other nonmetals, right? So compounds with anions of other nonmetals. So for example, if we have a compound like this, NaNH2, right? A compound called sodium amide, right? The sodium is positive, so the nitrogen is negative, right? That is an anion of a nonmetal. If we put a compound like sodium amide in water, right, the negative nitrogen takes a hydrogen ion from water and makes ammonia. What's left of the water, since it lost a hydrogen ion, is a hydroxide ion that is aqueous. And then we have a sodium ion as well. And so a compound like sodium amide is a strong base because the yield of hydroxide ion is equivalent, right? The number of moles of hydroxide ion you get is equivalent to the number of moles of sodium amide, right? We sometimes can see something like a carbon, right? The lithium is positive, which makes the carbon negative. This is called methyl lithium, right? But again, if that is exposed to water, right, the methyl lithium, right, the methyl group will act as a strong Bronsted-Lowry base, take a hydrogen ion from water, make methane, which is a gas, leaving behind a hydroxide ion in the water, and the lithium ion in the water. Now you have to be very careful with these because these reactions are very exothermic and can be violent. So whenever we've got some of these other strongly basic compounds, we have to be very careful to exclude them from water most of the time because these reactions can be very violent. So those are our major classes of strong bases. Okay, so now we've got to consider our common weak bases. Now, unlike, with acids, we had strong acids and weak acids. They all had hydrogen ions to donate, right? With weak bases, right, there are didn't want to do that. Reset that. There are no, stop it. Somehow my wrist is making it resize, right? There are no, stop it. Okay. There are no partially dissociating metal hydroxides that we encounter, okay? So we don't have the same situation we had with acids, right? So since we have no partially dissociating metal hydroxides, we have to look at other kinds of compounds that fit the definition of bases, right? And so mostly what we have to do is look at common compounds, right? So we have to look for compounds that react with water to create hydroxide ions as our common weak bases. And mostly the compounds that we will deal with that fit that are compounds of nitrogen where we have three things attached to that nitrogen. It has three bonds and a free unshared pair, right? That is our most common structure to lead to a weak base. So whenever we see a nitrogen with an unshared pair in its Lewis structure, we are going to assume that that is going to act as a weak base, right? That will react with water to create an equilibrium, and that we will then get, right, our conjugate acid, right? We will protonate our nitrogen, and then we will end up then with hydroxide ions. And because these are equilibrium reactions, our yield of hydroxide ion is lower than the concentration of the nitrogen-containing compound was at the beginning, and so then these qualify as weak bases. Okay, so examples of things that we will encounter as weak bases are really anything where we have that structure. So ammonia is one you should know, right? Right? Ammonia is a weak base. And then any substitution, right? So we can have something like, stop it. Why does my finger make it jiggle like that? So we can have something like Right, if we put a CH3 group in place of one of the nitrogens, that would be CH3, NH2, right? If we drew the Lewis structure of that, we would see, right, the key here being, right, this unshared pair of electrons, right? That is methylamine. Right? And so we could have methylamine, we could have dimethylamine, we could have trimethylamine, just keep replacing those hydrogens with other groups, right? A compound like this, right, with a nitrogen in a ring with double bonds, right? And then, if you're not familiar with this notation, every corner is a hydrogen or is a carbon, and there's a hydrogen on there to complete, right, its octet. But here this nitrogen has an unshared pair, right? This compound is called pyridine. And it is C5H5N, if we do its formula. And pyridine is a weak base. Even something like this, right? 6-membered ring with 2 nitrogens, 5-membered ring with 2 nitrogens, right? Put a methyl group here, double bond here with an oxygen, a methyl group here, a double bond with an oxygen there, a double bond there, and a double bond there, and a methyl group off that nitrogen. Actually, I think I need to change my double bond here. It's got, that nitrogen has too many bonds. Let's take that one out and put it here, right? That nitrogen right there has an unshared pair. Even with all that going on, that compound is a base. And oh, by the way, that is caffeine, right? So caffeine is a weakly basic molecule. So in general, most of the things we're going to see in this class, in general chemistry, that are weak bases are these compounds of nitrogen with an unshared pair, right? Nitrogen with an unshared pair usually is going to create a weak base. And that is one of the common groups of weak bases we will see, right? The other major group of substances that we will deal with that are weak bases are salts, right, of conjugate base anions of weak acids, right? So ionic compounds made where the anion is the conjugate base of a weak acid. And so if we look at something like sodium acetate, right? Where the acetate ion is the conjugate base ion of acetic acid, right? So we know that as a sodium salt, right, as a sodium salt, that sodium acetate will dissociate completely to create sodium ions in the water and acetate ions in the water, right? If we put this in water. But the problem is that we know that if we started with acetic acid, it would want to create an equilibrium with acetate. That's what makes acetic acid a weak acid. Well, anytime acetic acid is in solution, it wants to have an equilibrium with acetate. Equally, anytime acetate is in water, it wants to create an equilibrium with acetic acid. So in this case, our acetate will react with the water that it's in to create an equilibrium with hydroxide ions being created as the acetate takes a hydrogen ion to make acetic acid. Right? So whenever we have the salt of a conjugate base anion of a weak acid, when that dissolves in water, it will act as, right, a Bronsted-Lowry base. It will take a hydrogen ion from water, the Bronsted-Lowry acid, to make the hydroxide ion a conjugate acid, and acetic acid, I'm sorry, I can do this, a conjugate base, right? Acetic, or the hydroxide ion is the conjugate base of water, and acetic acid, which is the conjugate acid of the acetate ion. And, right, the yield of hydroxide ion is very low. It's very much less than the amount of acetate, and so this counts as a weak base, right? So anytime we have that situation where we have a salt, right, an ionic compound made from the conjugate base anion of a weak acid, when that dissociates in water, that conjugate base anion will act as a base, creating at least a little bit of hydroxide ion, and so it counts as a weak acid. So we always have to be aware of those things that are weak acids and what their salts would look like to recognize when we can have those types of weak bases. So those are our types of basic compounds that we will encounter most of the time in general chemistry.